Oh, there now it's off.
Yeah.
Was it recording?
Okay, so this is lecture 12, 2015, mainly Fourier Transform, and it's Thursday? 24th September. Okay. All right, let's start with questions. Is there a question?
Something you wrote at the end of last session, just before the Delta functions. You were doing some integral and you had x minus infinity. I wasn't sure what you were doing.
Where did that occur?
You wrote it before.
Is that the same question?
Assuming it is
Is there an equation in the book you want to point to?
No, I couldn't find it in the book.
All right, well, it's not in the book, it's not true.
It's just above. It's just below 2.105.
the Bible.
Just below 2.105.
2.105.
Oh God, I didn't even bring that chapter with me. Look, let's, why don't you see me after class?
Okay.
2.105, yes.
But then you have some integral with e to the I and x minus infinity.
It's going from 0 to 2 pi. In 106, the interval is 0 to 2 pi. Look, why don't you come see me after class?
My question does not deserve candy. If we find out typos in the book, then
Tell me, yes.
Then do we get candy?
Yes, you get candy, but you have to come to my office to get candy. I have a typo page, you know, that's, I try to keep up to date. And on this typo page, I give credit to third parties who, you know, point out typos. Thanks for doing boards.
Let me candy in itself.
Okay, let me, I guess I'm going to skip the last two sections of chapter 2. I think you can read them on your own, or last three sections actually. They're not specifically about the math, but I think they're worth reading, but I think in the interest of covering later material in the book, we ought to just move ahead. What I'm going to do, though, to start with, is I'm going to repeat what I did in the last 15 minutes of last time, because the derivation of the Fourier Transform business is probably something that you may need to see twice. Also, there's a pretty serious typo in the book that I want to fix. So basically, with the Fourier transforms, what we have is f of x is the sum n equals minus infinity to plus infinity, f sub n e to the I 2 pi n x over L, square root of L, and then the inverse relation is an integral from minus L over 2 to L over 2, f of x e to the minus I 2 pi n x over L over square root of L dx. And so the way I think of this is to use the nearest integer function, and that's y is, well, it's n if the absolute value of y minus n is less than a half, say, and you just sort of fish around among the integers till you find one that satisfies this, and that's what y is. So it's the nearest integer function. It's, I think, a standard function in Fortran and probably C with the right library. And what I'm using this for is to convert f sub n, which is a function that maps the integers into the real numbers, into a function, and I say here in the text, a continuous function. Duh, it's not continuous. In fact, it's just a function of a continuous variable, y. So I go from that to f hat of y, which is f of y. So now we've gone from a function defined on the integers to a function defined on a real variable, which varies continuously. But the function is still the same f sub n, and it's discontinuous. At least it's discontinuous if, well, it depends on what the f's are, but in any event, the point is that the thing that's continuous is the variable y. And in terms of this f of x is then a sum n equals minus infinity to plus infinity. And now what we can do is we can rewrite this fn as an integral over its constant values. So what we're doing is just going from n minus a half to n plus a half f hat of y e to the I 2 pi nearest integer x over L divided by square root of L dy. And this, since we're summing up over all of these, and each one is a, notice I didn't have to fiddle with this because this is an integral of length dy being 1. We go, I mean, the integral of dy is 1 because we're going from n minus a half to n plus a half. This is constant because it's defined in terms of this thing that's constant in this interval. So this is just an identity there. And now we can rewrite it as minus infinity to plus infinity f hat y e to the I 2 pi nearest integer x over L square root of L dy. So far, I've just rewritten this in what you might say is the most obscure and bizarre way of rewriting this formula. And it's often true that in mathematics and maybe in physics as well, that one makes progress by doing something silly, that is apparently silly, or taking a step backward. Now the point is that since y appears divided by big L, and we're taking the limit, bigger L goes to infinity, the difference between y and the nearest integer to y is divided by L is ignorable. It's trivial. It's something like 1/2 divided by L. And consequently, the difference between e to the I 2 pi greatest integer y x over L minus e to the I 2 pi y x over L, this is of the order of pi absolute value of x divided by L, and we're taking the limit L goes to infinity. So that's why we can replace nearest integer to y by y itself. And when we do that, we're essentially done. So in other words, this transition has been to rewrite this Fourier series in a very bizarre way, and then replace the nearest integer to y by y itself. And when we do that, what we have is f of x is an integral minus infinity to plus infinity f hat of y e to the I 2 pi now yx over L square root of L dy.
So, and I'm sorry, that absolute value approximate equality that you wrote down relationship right there is not apparent to me why that's true. Could you motivate that a little bit? Could you elaborate on that?
All right. Okay, well, let's suppose that y is, I mean, in the worst case, y differs from the greatest integer by a half. Okay. So in other words, we can write y here and y plus a half there. So then we have the absolute value of e to the I 2 pi y plus a half x over L minus e to the I 2 pi y x over L. Right? And we can rewrite this thing, we can factor this term out, this exponential. So this is e to the I 2 pi, well 2 pi divided by 2 is just pi. Pi x over L minus 1. Now we imagine that L is huge, so we do an expansion of e to the I that, and the first term is 1, the next term is that, and so this is I pi x over L plus higher terms. So that's it.
Oh, okay. I wasn't. Okay.
Physicists are always doing things like this. It's the way we make a living. It's like dogs barking. Okay. And now the next step is to change variables so we don't have to have this awkward expression y, 2 pi y over L. That's kind of a mouthful. And so what we do is we set k equal to 2 pi y over L, or equivalently y equal to L over 2 pi k. So we make this change of variables. We're going from y to k. And when we do that, what we get is, of course, dy is L over 2 pi dk. And so we're going to get a factor of L over 2 pi there. And we're going to get f hat of y. Well, of course, y is lk over 2 pi. And then we have e to the I, well, at this point, it's e to the I kx, which is just fine. Then we have L over 2 pi dk, and then there's the square root of L. All right, and if we cancel that a little bit, what we're going to have then is an integral of the square root of L over 2 pi f hat of lk over 2 pi e to the I kx dk, and we have this 2 pi fetish, so we have a 2 pi there. All right, so at this point, what we do is we say f tilde, which is the Fourier transform of x, f tilde of k, is this structure here. Square root of L over 2 pi, f hat of lk over 2 pi. And now if we remember what f hat is, f hat of y is just f of the nearest integer to y. And so this Fourier transform variable, to relate it back to this other expression, is square root of L over 2 pi, f of nearest integer 2, lk over 2 pi. So that, where this is the Fourier series coefficient. All right, so this is really the important relation, and in fact, I think in equation 3.6, I have these two terms. I should have added this term just to help the reader out. Once we do that, though, this f of x is just equal to an integral minus infinity plus infinity f tilde of k e to the I kx dk over root 2 pi. So that's our Fourier transform relation. So we've gone from the Fourier series representing the function as a series to representing it as an integral. And this is a kind of progress because you see this thing here is automatically periodic with period L. And whereas this thing over here has no particular periodicity at all. So we've now gone to the representation, the faithful representation of ordinary functions on an infinite interval. Whereas here, we simply have the faithful representation on the interval from minus L over 2 to L over 2. Because if the function wasn't periodic, it just, the series just goes bananas outside the interval. Let's see, is anybody paying attention to the camera? Because you have all this stuff. Oh, you had it there?
Yeah, you
Great.
were pointing up there.
I'm not paying attention to the camera, so I'm glad you are. Okay, now let's get backwards and let's find out find a formula for F tilde. Well, of course, we know what F tilde is. It's related to this. So I'm going to depart from the notes slightly. Well, maybe not. Maybe it's best not to depart from the notes. Actually, this formula that I said I should add, it appears in the very next line. Okay, so F tilde of K is square root of L over 2 pi. F at the nearest integer to LK over 2 pi. And that is, of course, square root of L over 2 pi. And we now use the Fourier series formula, namely this integral. And so that's the integral from minus L over 2 to L over 2, f of x, e to the minus I, 2 pi, nearest integer to LK over 2 pi, and then x over L, and then divided by square root of L dx. So I'm just using this formula directly, just substituting for n the its value, namely the nearest integer to the LK over 2 pi. But now we see we've got something in that's quite nice, because if we once again drop the nearest integer business here, then the L's cancel, the 2 pi's cancel, the square root of L's cancel, and what we get here, letting L go into L to infinity, we have minus infinity to plus infinity dx, e to the minus I kx dx over root 2 pi. And you may hesitate a bit. You may say, oh, there's a big L here. It's not fair to cancel this. But in fact, this is just some integer. And the error we make is not the whole value of the integer. It might be 65,000. It's the difference between 65,000 and 65,000.5. That's the biggest error that we make. And so it's the 0.5, but then the error is just 0.5 over L. So, and then it's the same thing that we talked about. So, this then is the inverse Fourier transform relation. So these are the two relations. Number 2 is this one. That's the inverse relation. And so let me just try to get the, well, I guess it's just this very long equation, which is just absurdly long, so maybe I'll write it this way. So so those are the Fourier transform relations, 1 and 2. And to relate Fourier series coefficients to Fourier transform coefficient, you use this expression, and it's most easily written this way. So I should maybe put this as equation 3. So this relates the Fourier series coefficients to the Fourier transform function. And then the Fourier, this is...
Oh, I'm just waiting for astronomy lab. I was just curious what you were doing.
Yeah, we're doing Fourier transforms. And you're welcome to sit down. There's a couple extra chairs. Anyway, so the function is represented as a Fourier transform. This is its Fourier transform, and you can write it then as an inverse Fourier transform. Or in a sense, actually, the terminology that's most common is that this is the inverse Fourier transform, and this function is the Fourier transform of f. And this is the relation between the series and the series Fourier series coefficients of Fourier transform variable. Now, a couple of things. First of all, there are the 2 pi's. You can put the 2 pi's any way you want, just don't change your convention in the middle of a calculation. Okay? So you could have no 2 pi here, no root 2 pi, then you'd have to have a full 2 pi there. Or you could have no root 2 pi here, full 2 pi there. Then you have a plus sign here. You don't need to memorize that. You can make it plus or you can make it minus. But if you make that one minus, this one's got to be plus. So there is this arbitrariness. Let me see if I can find some. Yeah, question.
So the coefficients of the Fourier series, is that as we're relating it to the function, is that as L goes to infinity, or is that just all, or just L?
Hold on a second. Where?
So equation 3,
Yes.
is that as L goes to infinity, or is that just L?
Great question. Here, we actually, you see, what is this? This is the Fourier series coefficient. So if you're doing the series, you have a finite interval. So L is finite. But that's a superb question. I should give you a second candy. I'll get way over there. All right. So once again, let me just mention this business of going from Fourier series to Fourier transforms and back again. If we have the Fourier series, we have f of x is the sum f sub n e to the I 2 pi n x over L square root of L. Okay, that's the Fourier series. And if we want to write that as a Fourier transform, we do this. We say f tilde of k e to the I kx dk over root 2 pi. And then you might say, well, if you already know what these are, you can guess what this is supposed to be. And in particular, you just use this formula over here. And you say, let me see, am I really going to, is that really going to do it? I think it's going the other way that it really makes sense. Namely, that if we have f tilde of k, so we actually have the Fourier transform function, then we can figure out what the series is by saying that fn, so in other words, f squared of lk over 2 pi is square root of 2 pi over L f tilde of k. And so in other words, we go from, if we had the Fourier transform relation, we get as the Fourier series a sum of things square root of 2 pi over L And now our f sub n would be f tilde of the k. And what would k be? Well, the k is, there's 2 pi, because I'm departing from the notes, which is never a good idea. But, yes, this is n. So n is Lk over 2 pi. And so let's see, f sub n is f tilde of k, and the k is, yeah, this is 2 pi n over L. K 2 pi n over L. So this is our series So I've got the phase factor over square root of L. F sub n is an extra square root of 2 pi over f tilde of k. And of course, using this relation, k is 2 pi n over L. And so this is, it's square root of 2 pi over L, sum on n, f tilde of 2 pi n over L, e to the I 2 pi n x over L, right? And yeah, that's what's that's equation 313. Okay, so I've sort of done it a little bit differently since I've ad-libbed it. All right. Okay, next, the Fourier transform of a Gaussian. Well, the rule is the Fourier transform of a Gaussian is a Gaussian. The proof of it is best done, as far as I know, using complex variable theory, and we'll get to that in chapter 5, I think. And so let me just assume a certain Fourier complex variable result. But first, let's start out computing the Fourier transform of Gaussian. This will be integral minus infinity to plus infinity dx over root 2 pi e to the minus I kx minus m squared x squared. Okay. Now, what you do in this kind of situation is you complete the square in the exponent. In other words, you write this as a perfect square. So to save blackboard space, I'm going to do it this way. Minus infinity plus infinity dx over root 2 pi e to the minus m squared x plus ik over 2m squared squared. Now you see the leading term, x squared, gives you that. The cross term gives you that. And then this term gives you something new, which you have to cancel. This will give you e to the m squared k squared over 4m to the 4th. And so what you need to cancel that plus term is an e to the minus k squared over 4m squared. Okay, so the equation reads this way. F tilde of k is equal to this after you complete the square. Okay, now here's the trick with complex variable theory. If you imagine this integral is an integral on the real line from minus infinity to plus infinity. But this is basically the nicest function ever. Okay. This is an analytic function, and it's analytic everywhere. That means that this is a remarkable result in complex variable theory. Namely, that if you integrate an analytic function around a closed loop, you get 0. The integral at very high x is obviously 0, because it's e to the minus m squared x squared. that interval is also 0. So if you do this integral in the complex plane, from minus infinity to plus infinity on the real axis, up a little bit in the imaginary direction, back at where x is equal to, actually I should have gone down rather than up. Well, I didn't look at the notes. Something I normally say to students that if my left arm is down when I'm lecturing, you need to watch for typos very carefully. The left arm is up, you don't need, it's not so much of a problem. All right, so let me just make some small changes here. This is the integral along the real axis. We then go down a little bit in the imaginary direction, go back along, not the real axis, but the real axis, x minus ik over 2m squared. So we integrate along this, back, and then up here. These two integrals are 0, because x is effectively infinite, and it's e to the minus m squared x squared, so it's super 0. So since the whole circular integral is 0, this integral is the same as that one, because the sum of the two equals 0. So what we can do then is we can take this integration here, this integral, and we can say, it's e to the minus k squared over 4m squared, integral dx over root 2 pi. And now, if we let x go to x minus this thing, well, we just have m squared x squared. And of course, this integral is a very simple integral. It's just e to the minus k squared over 4m squared, which is the thing out here. This thing is just a number, and the number is such that this is m root 2. By the way, this is a general property of Gaussian integrals. After you complete the square, what happens is you cancel, so you complete the square and you get this. This term comes out here. This thing is a function of k. The k dependence is here, and it looks as though it's here, but it's never here, because you can always shift this guy so this one goes away. So there's no k dependence here. This is just a number. All the k dependence is there. And that's true of all Gaussian integrals. And in fact, it's why I transform Gaussian as a Gaussian. Okay, so this is the answer. Notice, though, that the two Gaussians are very different. The original Gaussian, if m is big, the f of x looks something like this. Looks like that, if m is large. On the other hand, if m is large, f of k looks like this. Okay, very broadly peaked, because it's e to the minus k squared over m squared, and m squared is big. On the other hand, if m squared is small, then the original function is simple, looks like, in fact, I should get colored chalk. I've got colored chalk here. Well, they're a nice color. Okay, if m is small, then the thing looks like this. But on the other hand, if m is small, then this one looks like that. So the Gaussian is such that when you take the Fourier transform, you go from broad to narrow or from narrow to broad. Okay. Now, what we ought to do, though, is use our Fourier transform formulas, which allow you to go in both directions. We have one formula to go from x to k and another one to go from k to x. So let's go backwards. and see if we start with this as f tilde of k, if we wind up with f of x, which was this thing. F of x is e to the minus m squared x squared. Well, our inverse formula would be f of x is minus infinity and plus infinity dk over root 2 pi f tilde of k e to the I kx, and using this formula for f tilde of k, we have integral dk root 2 pi 1 over m root 2 e to the I kx minus k squared over 4m squared. Once again, we complete the square in k, and when we do that, we get this e to the minus m squared x squared out in front, and the rest is dk over square root of 2 pi 1 over m root 2 e to the minus k minus I 2 pi m squared x squared over 4 m squared. Okay? All right, so once again, we can use the complex variable trick to shift the k integration, to let k go to k plus I 2 pi m squared x. Bingo, this is just k squared, and so our formula is f of x is e to the minus m squared x squared integral dk root 2 pi 1 over m root 2 e to the minus k squared over 4 m squared. Now this whole integral, of course, is just a number. There's no more x dependence. It's the same thing that I told you about before, namely that the x dependence, once you've completed the square, you can use a shift on the variable integration to get rid of the x, and then the rest of the integral is just a number, and the x dependence is all out in front. That's a very important property of Gaussian integrals. And by the way, if you ever deal with path integrals, you'll find that Gaussian integrals play a huge role in path integrals. And this trick is very important there. And so what we get then as our formula is f of x. Well, this integral, we have to do the integral. Right? Do the integral, I guess, means click on Mathematica or MATLAB or something. In any event, when you do it, you see this integral is just 1. So this is e to the minus m squared x squared. If we now use our Fourier series business, we can say f of x is, of course, it's e to the minus m squared x squared, but it's also 2 pi over L sum n equals minus infinity to plus infinity 1 over square root of 4 pi m e to the minus kn squared over 4m squared e to the I knx, and of course kn is this 2 pi n over L, so if I rewrite that, it's 2 pi over L sum on n from minus infinity to plus infinity 1 over m square root of 4 pi. And now this is e to the minus kn squared. That's 2 pi n over L squared divided by 4 m squared e to the I x 2 pi n over L. So this is our normal Fourier series, and this times that is the Fourier coefficient. some of you, let's say, if one of you is particularly eager and wants to do an extra credit homework problem, what you might do is use Fortran or something to sum this series and make a graph of f of x. In other words, how close is it to this? And of course, it's only going to be good within the interval from minus L over 2 to L over 2. But the question is, how well does it go? And, okay, so that's a suggestion. If you make the graph in MATLAB, I'd be very grateful, because I was thinking of doing this, but one of you does it so much the better. All right, let me go now to Fourier. Any questions? All right, Fourier transform of a real function. Well, suppose f is real, then the complex conjugate of the Fourier transform, well, it's integral dx over root 2 pi f of x e to the minus I kx, and all of this complex conjugated, and if f is real, this is just dx over root 2 pi f of x, but now e to the I kx. But this is just our formula for f of minus k. So what happens is, if the function is real, that doesn't mean that its Fourier transform is real. It's rather that its Fourier transform is such that if you take its complex conjugate, you get the value of the Fourier transform at the negative value of k. All right, there are then a couple of relations, a cosine relation. Well, all right, I'll write them down, but they're things that I say are exercises. So let me just write it as a, I'll just give you the answer. You can write this down, 1 over pi, 0 to infinity dk, minus infinity to plus infinity fy, cosine of k, y minus x, dy. And as I write that down, I'm asking myself, why would anyone want to do that? But in any event, you can also write this as 2 over pi integral 0 to infinity cosine kx dk integral 0 to infinity y cosine ky dy. This is if f is even. So if f of minus k equals f of k, and as 2 over pi 0 to infinity sine kx dk integral 0 to infinity f of y sine ky dy, if f of minus k minus then there's this, is the water due to a leak, or is it your water?
No, that was here when I sat down. I don't know. I think it was.
Yeah, this building has a flat roof, and I don't know why people do flat roofs, because it's just asking for trouble. If you do a pitched roof, then the water runs off, and there's no problem. But you have a flat roof. Okay, the next thing is Dirichlet's formula. This is basically just an example of a Fourier transform. Maybe I should draw the function. It's 1 and then 0. So this is minus 1, this is 1. So I haven't drawn this to scale. And, you know, we can say make its periodic extension, we just say it x equal to 1, it's a half. In any event, you can write it as a Fourier transform, and when you do that, if you massage the Fourier transform enough, you get 2 over pi, 0 to infinity, sine k, cos kx over k dk. And this integral, if you're mathematically inclined, you might worry a little bit about this integral, but it really does converge eventually. Another Fourier transform is e to the minus beta, absolute value of x. This is 2 over pi, 0 to infinity, beta cos kx over beta squared plus k squared dk. And on the other hand, the odd exponential, namely x over absolute value of x, e to the minus beta, absolute value of x, this is 2 over pi, integral 0 to beta infinity, k sine kx over beta squared plus k squared. Okay. All right, the next topic is Fourier, Dirac, Parseval, and Poisson. And so let me, in fact, I regret a little bit having spent so much time on all these integrals. Gaussian, of course, is of maximal importance, but these other things, seem one integral, seem more. All right. So once again, let's take one of those funny steps backwards. F of x, we write it as a Fourier transform. And now what we're going to do is the thing that seems crazy. We're going to write the Fourier transform as the inverse Fourier transform of the function, or maybe it's just, what you call inverse is a matter of case. Anyway, so what we're going to have then is minus infinity plus infinity dk over root 2 pi e to the I kx. And then f tilde k we're going to write as minus infinity plus infinity dy over root 2 pi e to the minus I k y f of y. Now, if you do this at home for the first time, don't set, just because we start with f of x, don't write f of x here. You want f of y here. But now what we can do is we can rearrange things. And of course, rearranging things is really rigorously true only if these are times functions. And when we're talking, when you hear the word Dirac, you have to think, oh, he's going to use the Dirac delta function. And of course, that means that we're really talking about functions that are smooth and go to 0 at infinity and suitably quickly. So in that case, we can massage things any way we like, and we get dy. And then what's left here is minus infinity plus infinity dk over 2 pi e to the I k x minus y f of y. And now we compare that. So let me just we compare that with the equation f of x is integral minus infinity plus infinity dy delta x minus y f of y. Both integrals give you f of x. So it follows then that this integral here is a representation of the delta function. And it's in fact the most useful representation of the delta function. So in other words, we write delta of x minus y is integral minus infinity to plus infinity dk over 2 pi e to the I k x minus y. Now, in this case, the 2 pi has to be there. Secondly, the plus sign here could have been minus, doesn't matter. And that's partly because, or that's consistent with the fact that the delta function is positive, and in fact it's an even function. In other words, the delta function it's a limit of something that looks like this, so it's perfectly symmetrical. Of course, that's thinking of it as a function. It's really a function. So it maps functions into numbers. Only if the functions are good. All right, so let's now think about the inner product of two functions. And a very nice inner product is an integral dx, f star of x, g of x. And now I'm going to fool around with this because I'm going to write f of x as a Fourier transform, g of x as a Fourier transform. And so what we're going to have here then is dx f of x star, that's going to be integral dk over root 2 pi, and then f tilde of k e to the I kx, complex conjugate because of that star, and then g of x is going to be an integral, let us say dk prime over root 2 pi, g tilde of k prime e to the I k prime x. And all these integrals are from minus infinity to plus infinity. Okay, but now this thing is an integral dk and an integral dk prime. So everything's minus infinity to plus infinity. And then combining the 2 pi's, we get dx over 2 pi. E to the I x, k prime minus k, f tilde star of k, g tilde of k prime. So that's what that is. On the other hand, we see that this thing here has the same form as that. It's just delta of k minus k prime. In other words, here we had x and y. See, x and y occur here and here. I'm saying that this is then delta of k prime minus k. And so this is integral dk, integral k prime, delta k prime minus k, f tilde star of k, g tilde of k prime. And just to reassure yourself, the argument of the delta function occurs there, just as the argument occurs there. Then you have ik, ix, dx, dk, 2 pi's. It's the same formula. And now, using the properties of the delta function to do the integral over k prime, we get that this is the integral minus infinity plus infinity dk f star of k g of k. And so what we get is that this is equal to minus infinity plus infinity dk f star k g tilde. So this is an important relation. It's that the inner product of two functions, or if you want in quantum mechanics, two states, it's the integral over x of f star g, but it's the same as the integral of their Fourier transforms. So Fourier transformation is effectively a unitary transformation. And that's why it can represent translations, because when you translate things, you take one system, you translate it in space, you've got the same system just in a different place. And in fact, some physicists like to do it more abstractly and say, well, we don't want all the pollution associated with actually moving the system. Let's just change our coordinate system. So that's the other way of looking at it. And of course, as a student, sometimes when you hear people talking about both, and you sort of can start wondering, well, where am I? Have I translated, or am I changing my coordinates? So it can be confusing. In any event, if we, well, first of all, this is Parseval's relation. So let me just baptize it. Parseval's. And in particular, if we set f equal g, then we get that ff, which is an integral of absolute value of f of x squared dx is equal to the integral f tilde of k absolute value squared dk. So this is the statement that something is square integrable, it has a Fourier transform, and the Fourier transform is also square integrable, and moreover, the two integrals are the same. So you can compute the norm of the function in x space or in Fourier transform space. All right, now a little more about delta functions. And I'm about to say something that is used over and over again in physics classes, and almost never does the professor explain what's going on. Of course, I don't know, maybe the other guys in the department sometimes that they explain what's going on. But in general, I don't think they should. All right, so let's consider something J. So we have a break here. Okay, break, new concept. J. And so far we've been talking about delta of x minus x prime, delta of k minus k prime. Now I want to say delta of g of x, f of x dx. So what is this? And so qualitatively, you can see that that is going to be essentially proportional to f evaluated at whatever point x makes g vanish. Because the delta function, if you want to think pictorially, the delta function has a huge spike when its argument is 0. So this is important only when g of x is 0. All right, let's suppose, just for simplicity, that g is a function that crosses the x-axis once. So g is 0 at a unique point. Let us say x0. Well, what that means then is that this is equal to, this is proportional to f of x0, integral delta of g of x dx. So we can pull out the f of x0, where g of x0 equals 0. Okay? All right. Now, also, whenever we are talking about Dirac delta functionals, we mean we are talking about nice functions. And so this thing is f of x0 integral delta. And this effectively is g of x0, which is 0, plus g prime of x0, x minus x0, plus higher order terms that we forget about because it's the physics department and we don't care about anything that's not leading order. Okay, so that's what we've got. And now we're going to do something that's a little bit silly. We're going to say, well, I'm going to write that as f of x0 divided by the absolute value of g prime at x0. Now this is delta of g prime of x0, x minus x0, absolute value of g prime of x0 dx. Okay, now this is, we're going to rewrite it again, f of x0, absolute value g prime of x0. And now I'm going to rewrite that as delta of g minus g0, and this is going to be dg. Whoops, sorry. Okay, but on the other hand, this integral is just 1, so this is f of x0 over absolute value g prime at x0. And I
have a question.
yes.
For this step, did you substitute the integration of dx with the function? How that works? So
Up until this point, everything is more or less clear, right? Okay. The point is that this is basically g minus g0, but g0 is 0. So this is, effectively, it's delta g, dg. The part that is a little confusing, and maybe I should have clarified this somehow. It's that well, let's look at signs. In the sign in the sense of SIGN, the only sign comes from this because delta is always positive. And we get the right sign by pulling this out. So we want this thing here to be positive, whatever it is. And so we say, well, it's this and this. And indeed, that's positive, this is positive, everything's fine. And now we can say this thing, all right, if I do it in a couple of steps instead of, I add a step or two. G0, of course, is 0, so this is really d of g. But this thing is really absolute value of dg, essentially. Well, it's absolute. All right, I must say I'm having a little trouble. Well, let's see. We took care of the sign. We know the sign is positive. The magnitude is obviously unity because we're integrating dg, delta of g dg. Apart from a sign issue, namely this absolute value here, this is dg. And we know the sign is right. The magnitude has to be unity, and so it's this. But I agree, it's once I put the absolute values here, in fact, what I probably should have done, here's the right way to do it. Put an absolute value out here, you know the damn thing is positive. Then you do this. And then you do that. And then you get this. So that's the better way of doing it. Okay, now, this was for the case of G having a single zero. Maybe it has several. We'll leave you some of them. So the real answer is that J is the sum over the roots of f of x0k divided by the derivative evaluated at x0k. So in other words, there might be several points, x0, k, k equals 1 to n, however many zeros there are. And for each of these, you just form this ratio. So you just repeat the thing around each zero.
So you say this in the book, that the derivative of g at the point where it's 0 can't be 0. But,
oh yeah, because we're dividing by it.
Yeah, but suppose, how do you handle the case where that is the case, like a monomial?
That's a marvelous question, and your timing is perfect because it's the end of the hour, so I'll be able to think about it over the weekend. So let me think about that. I don't know. That may be a case that is. That may be a case that's problematic because you surely can't divide. I mean, you want to divide. Well, all right. Let's suppose. All right. Let's suppose that simply the G prime is 0. Okay. So then what you'd have is G double prime, you'd have x squared.
G double prime evaluated at the point where G is 0, so what you're calling x0, x naught. And then
yeah,
x minus
G
x
double
naught
prime
squared.
at x0.
Yeah.
And it'd be a 1/2. And I don't know, I'm going to have to think about that because that's not a case that that I worked out in the book, and so I'll think of a great question. Yes.
Can you just go over the step from when you substitute G from G prime and inside the delta function? Yeah.
Well, G of x0 is 0.
Okay.
So G is approximately G prime at x0, x minus x0. So this is approximately G of x.
Yeah.
That's all. But then if you just think of it as G, and then this thing is dg inside the absolute value sign, then it's just the whole thing is 1. All right, but I know you were handy. Well, I better use my left hand because I'm somehow more accurate. It's amazing.
And then I got one more question.
All right, did you turn on? Somebody turn the thing off?
Yeah, it's